Okay, so this will be the final video in our chemical kinetics trio here, or trilogy. Um, so we just have a couple things left to talk about here. The first, we're going to go back over what happens to make a reaction occur. And the first thing that makes reactions occur are collisions, right? The atoms or molecules have to collide in order for the reaction to occur, right? They have to come in contact with each other. The second piece is orientation. So when they collide, they have to be arranged properly so that the pieces that are going to interact touch. And so not only do they have to collide, but they have to have the correct orientation. And then the final piece that we're going to talk about in just a second has to do with energy. And so not only must they collide and collide with the correct orientation, but they also need to have enough energy. And the minimum amount of energy needed for the reaction to occur is the activation energy. And so activation energy, when we're thinking about this, right, don't think about it as, a direct thing. We're going to think about it as a graph, right? Because when we're talking about energy and here kinetic energy, right, and as the kinetic energy or the temperature of a substance increases, you're going to have a larger amount of substances, right, that fall above the threshold for activation energy, right? So low temperature here, right, most of your molecules are below the activation energy threshold with just a small amount down here. Whereas when you increase the temperature, right, you have a broader range of kinetic energies in here, right? But you have a much larger proportion of molecules that are above that kinetic energy threshold. And so more reactions are likely to take place. And if we think about activation energy in terms of exothermic and endothermic, right? Endothermic over here on the left, right? The activation energy tends to be larger because you're having to put in more energy initially because the system is absorbing energy in an endothermic process, right? So not only do you have to put in enough energy for the end product, but you also have to put in above that, right, the activation energy. Now with an exothermic reaction, right, you put in the activation energy, but then actually your system is losing energy in the process, right? So the energy output is greater than the activation energy that was put in. And then if you think back to the previous videos where we talked about reaction mechanisms and we talked about intermediates, right? When we talk about intermediates and reaction mechanisms and reaction pathways, right? Often there is more than one activation energy for a process, right? So here we have activation energy 1 that leads us to our intermediate here. And then that intermediate, right, there is an amount of activation energy for the reaction with the intermediate that then goes on to form the product, right? So when we're looking at reaction mechanisms for full reactions, right, often there will be multiple activation energies that are going on because somewhere in the middle you're forming your intermediate that is itself going to need an activation and some amount of activation energy to complete that full reaction. And then, of course, I'm sure you were wondering if there's an equation that goes along with this. And yes, absolutely, there's an equation that goes along with this. It's the Arrhenius equation, however you pronounce that. So this is a form that you might see it in. And I want to make clear that this piece here is a exponent to the e, right? So it is k equals a e to the negative ae over rt, right? And don't confuse this a and e with this a sub e, because these are two separate things, right? We have e, our lovely letter that has a specific value, and we have a here, which is different than activation energy, right? Up here. So in this, all right, K is our rate constant like we have been talking about. A is a frequency factor that is nearly constant at a given temperature. The A sub E is activation energy. All right, T as most often temperature, and then R here, our ideal gas equation or ideal gas constant, but this one is specifically in the 8.314 joules per mole Kelvin, right? Because we're dealing with energy, so we have to have that unit of joules. All right, so that is one form that you might see this in. Sometimes you will see this in a linear form, right? Where you have your approximation of y equals mx plus b, right? So that is the Arrhenius equation in linear form. And then the most often found version of it is when you are comparing things at two temperatures, right? You have two temperatures, you are using those two temperatures to figure out the activation energy that's going on here. So you will have two rate constants that apply to two different temperatures, and you are able to calculate the activation energy that way. Okay, that is the equation. Now, catalysts. And I am sorry, right? This doesn't have anything to do with cats. Unfortunately, I know as much as we all love cats, doesn't really have to do anything with cats. However, a catalyst does have something to do with reaction kinetics. So what a catalyst is specifically is it's a substance that changes the speed of a chemical reaction process without undergoing a chemical change itself, right? So it speeds up a reaction but is not changed as a result. Two types of catalysts, homogeneous catalyst, right? This one's going to be in the same phase as the reactant. So like say your reactants were liquids, you would pour a liquid catalyst in. That would be a homogeneous catalyst. And then you have a heterogeneous catalyst. That's going to be in a different phase than your reactants. Most commonly, what this is going to be is it's going to be some sort of solid that is used to catalyze a reaction involving liquids or gases or both. How exactly do these work? So, one way that they work by offering a new reaction pathway, right? So some new mechanism. They insert themselves into a mechanism. You probably make some sort of new or different intermediate, and this is usually how homogeneous catalysts speed up reactions. Another way is they help to achieve collisions and the correct orientation more easily. All right, this one usually involves a heterogeneous catalyst. One very important type of heterogeneous catalyst, or a catalyst that works in this fashion, are enzymes, right? So hopefully when you took biology, you remember talking about enzymes and how enzymes speed up the catalyst or the chemical reactions in our bodies by grabbing and holding on to molecules. Often it's called the lock and key model. You'll see something like this where your enzyme is drawn and you've got like a square piece here and a triangle piece here, and it grabs, triangle molecules and square molecules and holds them together in place and facilitates that reaction, right? And that's really good for living things because without enzymes that speed up reactions, we would not exist. So thank you, enzymes. And then how these work in general. So basically, you're generally lowering the activation energy requirements of the reaction. And how we usually show this is if we have our diagram of, let's say, an exothermic reaction, right? This will be before the catalyst, and then after the catalyst, you'll have this dotted line here with lower activation energy, all right? And you'll see something like without catalyst, and then with catalyst. That was supposed to be a W, but I'm out of slides. And so that means we're done with this video, and I will see you in class.